The original title was the tomography thing, but then I realized that it would be interesting to look a little bit of the background on how we end up doing that. So let's go for it. Okay, you know this one basically means exactly what it means for you, that whatever I said is just me and not Shell, you know, so let's go. All right, the agenda, so a little motivation, but at this point now, after Kenton and Anarco Fox presentation is basically the same motivation, more or less. The new stuff is that I'm going to introduce the fault detection part that I didn't have before, and then the tomography part. The color code here is basically people that collaborate with me at a certain point in time to make this happen. I basically work with two different teams in MIT and some people from Stanford and my colleagues from Shell. So, okay, so this is the one that everybody more or less agree or disagree to a certain extent, but everybody has in their mind at this point out. We have this revolution coming. I've been here for some years now. Some people are taking advantage of it, some other not. They're still thinking, hesitating, or whatever. But I think we cannot miss this one. This is really big. It might change fundamentally the way we do things in the industry. Okay, so let's go to the meat of it, right? So the classical way to do exploration on the geophysics, geoscience side of it is to start with some accrued data, acquisition, raw data, then pass through different stages until you get to a model that more or less all the domain experts will agree that's good enough to make decisions on it. That's the classical way to do. It's heavily in human intervention. And has been worked out for many years. And this is basically a legacy workflow at this point out, with minor differences respect to the industries, right? So, and then you have some kind of loop back. Feedback is workflow there, and so on. So we thought, okay, what if we do this? What if we go straight from the data to the model? So, there's a silence. Yeah, it sounds like crazy. Bold, far-fetched, moonshot, you name it. But we were looking for that. We were looking for a problem that is really tough, but may pay off big. So we start working around this idea. Then the loop is still there, but it's a shorter one, or faster one at least. So that's basically the main idea. So how we formalize this a little bit further, so we have the data, we extract some features from it, the one that we are interested on, and we train a machine learning model that then will infer, predict specific elements of a model. So that was the original idea. I get a lot of pushback by domain specialists that said that no way that this machine learning system will be able to capture such high-dimensional problem and nonlinear and so on. So then I just throw back the Hornick theorem. You can search by yourself. 89 or 90 is the paper, and basically states that a machine learning with enough coefficient will be able to capture any mapping, basically. So that's my theoretical defense for saying. And then into details. So for instance, at the very beginning, we decided to start with faults because it was one of the most well-known relevant elements in structural geophysics. But the problem was that we didn't have enough quality label data for saying a politically correct way. We didn't have good labels to train these models. And like you mentioned, garbage in, garbage out. And for machine learning, supervised machine learning, the labels is that part. If you don't have good labels, that's it. The performance, the accuracy of your model is going to be bounded by the quality of the label. So, okay, so what do? The only thing we can realize at that point was a path to go was to create models and labels from those models that we control. So we have full control of the experiment. We create the models. We have a generative process to generate feasible models. Then we obtain through modeling, which is the classical way of obtaining data, synthetic data. So then that's the data we use to then extract feature from. And on the other hand, since I create the model, I know exactly where the faults are, and I can represent them in a way that are suitable or amenable for my machine learning process. So these are the two streams, the data stream, the labeled stream. I have full control of both, basically. So I can at least, as a proof of concept, know exactly what I should expect and understand if this has a potential, right? So then you train the system, and then you go and predict with certain error bars or convention. So we present something like this, EAE 14, but at that time it wasn't neural networks. We were playing with kernel methods. It worked to a certain extent, but the main point was that, okay, we're trying this from raw data. That's never done before. Let's see what happened next. So, oh, of course, I pressed the wrong one. Which one is the one? All right, thank you. All right, so what we got, okay, so this is 2D synthetics. This is now 15, so we improve a little bit certain aspects of the problem. Now it's actually neural networks, not kernel methods. So we have this layer cake models, very simple with a huge fault. So the representation is something like this. Then the label or ground truth is something like that. And the prediction at that time was something like this. So here I'm overlaying the expected and the predicted. You see the gray little pixels there are the only places where there's a difference between the prediction and the expected. So we were very happy. In terms of qualitative and quantitative, pretty good results. Then we went and to complicate the problem, adding pseudo solve bodies. Then we might expect that the illumination-wise we will see nothing underneath, but still we were able to capture the faults. Then more complicated fault networks, and so on. So it looks like it worked for synthetics 2D, right? So what's next? 3D. So the models get more complicated. Now we are entering on at least on the data generation part in the HPC domain, because these models are huge producers of data, basically. And then you can see that we still have some interesting patterns happening in terms of faults and networks and so on. So when we got to this place, our architecture, neural network architecture, was falling short. So we had to do something, and we realized that the loss function that we were actually solving for was not the best one for the problem. We were not able to capture locality of the events well. So we designed a new loss function, which is called the Wasserstein loss function, and we published it in NIPS 2015. Pretty well accepted by the community at this point out. So results were like this. So this is the model, unseen during training, of course. This is the ground truth, the expected result. This is overlay of the fault system on the model, just to have an idea where the things are or how they should look like. And then we start to see this kind of results. So it's a little bit weird, but when you look at in detail, you see that they're mostly following the expected result. This is another one. Now 2 cross lines, and you can see the expected result here and the prediction. So we published that last year in the Leading Edge. I think it was the March edition, special edition about machine learning and data science. And it became the most downloaded non-free paper of the magazine. So I'm not put this there to brag. It's just to say that these things are becoming important, and people are starting to read about this and see if they has potential. And I think it's the path to go. One path to go, right? Actually, I think the second most downloaded one was from the colleagues from Prairie View, Texas A&M, you over there, your paper, yeah, which is somewhat comparative to what Analarco presented today in terms of interpretation. Yeah, this is HPC conference, so I had to put a little bit of the hardware and things, right? So we have a huge warehouse side where we produce data, with the data, the synthetic data that we are well sorted and clean, as you mentioned, and that's the advantage to have the synthetic data. It's perfect to work with, right? The flip side is that it's not that complex as the real data, of course, but then we mostly implemented our algorithms in Julia language and then TensorFlow. so then, therefore, the data set, the data types or file system is somewhat related to that. So HDF5 for performance and TF records to speed it up for the TensorFlow part. And all of the things we solve are basically run on GPU for reasons that you might understand. In terms of the flow, again, we have the models, we know the data, we train, and then we infer. So that part is the same. It's just to show where the things are in terms of technologies. Okay, so now the tomography part. So now we were at that point, we were like happy with the fault work. But fault is just one thing, right? And the end goal is to have a full model, a complete velocity model, fully predicted. So who does that? In our jargon is basically velocity model building. And velocity model building, you basically have FWI or tomography, any kind of tomography, any kind of FWI. So we decide to give it a shot. What if we, and now this is a completely different problem from the machine learning perspective too, because the previous one was a classification problem. I'm basically deciding at each pixel of the model, do I have a fault or not? Binary classification, pretty simple. I can do it multi-class, adding other attributes of interest. It's still classification. This one is different, because here the values in the model are scalar values. It's a velocity or impedance or any kind of scalar value that you want to determine. And therefore, now we're talking about regression. It's a different world in machine learning, much more uncharted territory for neural networks. So we give it a shot. Here the situation is somewhat different. For the training part, we still have to generate these models and obtain some data and do some extraction. But now the label part is different. There's not anymore a specific binary label. The label now is a full model, because that's what I want to have. What I'm creating with the machine learning part is create a nonlinear mapping between a model and data. Full model, data. So this is the training. Then the testing will produce new models not seen during training, and then exposed to the trained model and reconstruct the velocity model. So this leads us to something very close to image reconstruction world for placing in the academia jargon. And then deployment, we will use the real recorded data, right? And see if our tomographic operator, our trained model can actually reconstruct the models that we're expecting for. Right, so there's an important piece here, which is feature extraction. I cannot solve this for every feature in the data. It's just too high dimension. So I have to help the training to narrow in the element that is going to be trained, right? Reduce the dimensionality of the manifold will be the correct term. So in our particular case, since we work with pre-stack data, there's not so many attributes as compared to post-stack. But the one that is our interest is semblance, because semblance is the one that carries some velocity information. So it will help the neural network to solve the velocity mapping. The equation right here is by the book. It's the classical definition of semblance based on an MO-corrected image. And then we had to run some scanning to produce these slides, right? That's a typical way that semblance is produced. We add a third dimension. You can see like this. These two dimensions here help with the velocity part, but the third one will help you with the spatial part, right? Where this velocity is in the model, right? So I'm helping even further the machine learning training, doing this, applying this trick. Without this trick, we were not just able to converge. So this was the key for this particular problem. We published this result this year, 2 months ago, just to show where we are with this. And the results, I wanted just to acknowledge or recognize that most of the technology, we are like behind like 3 or 4 or 5 years with respect to other fields in this, okay? So like the medical imaging people, they are like far ahead. They are actually creating architecture that we then copycat, basically, right? This is one of them. It's a UNet. What they were solving here, you see that the picture doesn't look that different from our channels and so on, right? So that's why the inspiration came from, right? They were, I think in this problem, they were looking for tumors in kidneys or something like that, right? But the architecture is pretty useful and can be applied to our problem. So the results. So these are the first batch of results. The column here is the ground truth, what is expected. This is the prediction. And the other two columns are post-process, optional post-process that we run on the prediction. So we can see that in general terms, we are recovering the structure. And more importantly, we're recovering the velocity, pretty close to what is expected. The other two columns are basically we thought, okay, what if for whatever reason you know how many layers you have, major layers, and we impose a constraint based on a clustering algorithm to recover even that. So you see that, let's say I know these 4 layers, so I ask for 4 layers, and it will recover the 4 layers, and they're pretty, really close to the original. But these are just gain for synthetic. It's not going to happen in real data, but it was interesting just to do it, and so on. Some of the models even have faults. That we didn't recover. That's really hard. I mean, you don't recover faults with any velocity model building that I know so far. So that's tough. That was last year. Now we got it. I'm not going to show it here because it's in the press, but soon we're gonna have results with that too. All right. Then, okay, more interesting. What about if I have solid body on it? Right, then the thing gets really interesting. So let's say I have just the layer cake thing. I still recover the major structures and the velocity, but now I have this kind of solid body. This is a different data set. This is a generated, synthetic generated, pseudo-random generated model that then is augmented with these solid bodies that come from quote-unquote real velocity models. So this is halfway to real data test. And you can see this is the expected result and this is the prediction, and it's recovering pretty good. I mean, for what is from, remember, this is not SWI. There's not an initial velocity model here. I just present a training model with the data, and it produced this in 1 second. Okay? So that's what we're talking about here. This is another case, another solid body. This one is even nicer. So how this is happening? I mean, so what I did to sort of picture what is going on is during training, I test the trained model, the model that's in training, with a specific velocity model that is not in the training set, which is classical in statistics. This is basically validation. So during validation time, I present this model every certain number of epochs, which is basically the training steps in machine learning, and I recover a model to see where is the prediction going for this particular case, right? So after 10 epochs, which is almost nothing for what I need to do for train these models, you see that it's nothing. It's kind of a layer gradient-based cake, I will say. The velocities are not that far, but there's something there. All these dark blue dots are dots that are just not even resolved yet. It's learning to resolve this, right? After some epochs, like 30 epochs, things start to happen. You see that here is kind of flatted layers. Here, realize that there's some kind of dip here, which is there. And then it's realized that there's some high velocity event around here. Doesn't know exactly how or the shape of it, but it realized there's something. So it's progressively improving. Then 50 epochs, the bodies start to really get narrowed down. And then after 100 epochs, it really nails the solid body there. I still have doubts about what to do here. You see, it's, you see there, it's a little bit, I don't know what's going here, but it should be something like this. And then 250 epochs is usually where I stop. The solid body is pretty much there. There's some dips, and even this guy here, which is a high velocity one, is recovered. So this is kind of the way this is learning. What else do I have? yeah, that's kind of qualitative analysis, more quantitative. For me, it's really important to do quantitative analysis because otherwise I don't know if I'm improving, right? If I just look at the picture, I look better, but how much? You know, I mean, you have to have some quantitative metrics to evaluate your progress. We decided to rely on two for this work, R squared, which is a statistics metric, basically about confidence on your predicted model, and SSIM. SSIM is different. It comes from the image reconstruction world. Basically, it's the structural index similitude, the structural similitude index. That's SSIM. It looked for similitudes between models at different levels. So it's basically like a moving window within two models and look at how the local windows look at each other, right? So we can see here both max at 1 and R squared for nonlinear problems like this can be negative, right? SSIM is actually somewhat logarithmic, so the difference between little changes are huge in terms of performance. So what we can see here is that these are the epochs, training epochs, and this is the metric value. We can see that SSMI, it's pretty good even from the very beginning. We might think, okay, wait a minute, but if you go back, you see that the very beginning is not even close. How this is good? Yeah, this is one example, and I have like 1,600 for evaluation. So some others get it almost immediately. That's why the metric is good even at the very beginning, right? And it's stable along the training set iterations. The other one, the R squared, it changed a lot. At the very beginning, it's not really good. But after some time, it starts to converge. And at the very end, the last 200 epochs, you can see that it's still getting there. So we get up to like 0.7 for R squared or something like that, which is pretty good. It's pretty remarkable for people who are familiar with this metric. The different curves coloring are related to different experiment setups for the machine learning model, so different mini batches in our case. Right, so that's pretty much what I have. Conclusions, I agree with most of what you said, except the ones that are particular to my problem, which is what I'm saying is that we obviously have to do real data, and we got to go to 3D and so on, but the proof of concept is pretty compelling. I mean, if you guys are not somewhat convinced that this is kind of working, it's up to you, you know? So what you have to do next is to put your people to work on this. Maybe not specifically this one, but similar problem that will add value to your organizations. Now then the discussion is what value you're actually adding. And that's a good one because there's many angles, right? Is it about cost? Because you're dramatically reducing time, turnaround time, right? Think about this. This whole training 300 epochs, and for this data set takes 5-6 hours and one computing node with a couple of B100s. And then that's for training. Then the inference takes, for 2,000 testing, it takes 30 seconds. So imagine the uncertainty quantification techniques you can apply. Imagine all the scenarios you can play with. I mean, this is another world, basically. So that's one of the angles, right? You're going to get a lot of fast turnaround with this that you didn't have before. The other is about accuracy. And that one is much more tough, right? So what I'm doing right now is actually comparing head-to-head with FWI for certain tough problems, because people will ask how this stands with FWI. And we are actually analyzing that. And if everything goes well, probably for SEG, we will have the first results. So you have this other aspect, right? Quality. And finally, it's about, if this is going to happen, you need to prepare your people. This from the very beginning, from the pipeline of where you're going to get your new people and how these people are going to be trained, are going to be data science or geophysicists or geophysicists that know data science. We had this discussion about HPC like 6 years ago. It should be a geophysicist that is good HPC, or it's an HPC guy that works with geophysicists. I don't care how you do it, but you people should be getting into these kind of problems and as soon as possible. Thank you.
Hello, we have time for 1 or 2 questions.
So just since you are using semblance and kind of like in your results, so why not to use the wisdom from our tomography and FWI, because you are kind of trying to compete with FWI or the preconditioner, but why not to find a hybrid
Yeah, like
solution?
I said, this is much more faster, you know. You know, FWI, how long it took to actually get where it is right now, like 20 years, right? And still for real data, it's pretty tough, right? I'm just put it that way.
A question back here.
But you know something, they can be combined. That's where you're going. Oh yes, oh yeah, absolutely. Yeah, we're looking at that too, like use this as a preconditioner for the FWI convergence or vice versa or something, yeah.
Question here.
Yeah. Oh, so first of all, I would like to thank you. You're one of the few people in this industry who's actually speakingly, openly what you're doing, and this is really valuable for all of us. Now my question. I think that's actually worth a round of applause. Now here's my question. What we keep seeing is people working on synthetic data for obvious reasons. So how do you want to get out of this? Because when I look at the machine learning methods that are available, there's not much in the arsenal in terms of combining simulation and deep learning. How do you want to get out of there?
Right, so internally we have an effort now to prepare data sets, real data sets with the correct labels and so on to really test this and put it in deployment, right? That's internally. As an industry, hard to say because people don't share data here, right? And that's the reality. Some ideas have been floated around, like use the SIM consortium as a conduit for this. You can imagine you can take the SIM models as they are right now, apply some random variables on them, and generate a bunch of models for which you have the label data, and then create a competition that everybody can go and try to win, right? That would be an idea, yeah.
One final question here.
Yeah, for classifications with deep learning, what is the size of the data? The data set
Oh, that's a good one. For the 2D, because we start with really small models, we have like 40,000 models from which we get data. So that was the order. For tomography, it was much more or less. And we work a lot. There's some tricks, some black magic here to reduce dimensionality as much as possible, right? Definitely, we are not in the millions of models or pictures like MNIST or the classical benchmarks. So yeah, it's in the order of 40K for classification or something.
Thank you.
Please join me in thanking Mauricio again.